Okay. Let's continue from last time. Okay. So this is nowadays a storage architecture, right? So a little bit. This is CPU. This is a main memory, and what's new is something called a non-volatile memory. Right. The goal is that when you go out of power, when you power it off, right, the current memory cannot hold the content, but this non-volatile memory can hold the content. Right. So which means, right, when there are not much workload, we can turn off the servers. Right. But in the current technology, if you turn off the server, next time you turn that on, it takes a long time to load all the data into the memory. Right? But now you don't have it. This 3D is trying to make it multiple layers of memory to make it even larger. For the disk, right? Traditionally they have the flash. Right? This disk is I mean, probably in the desktop they have a disk like this. Right? So there are some tapes inside, and there are some rotating rotators there. Right? There is a header try to rotate you to the right location to read the data. But the problem of the traditional disk is that first it's slow. You can imagine if what you want to load is far away from the current position, it takes quite some time to get there. Also, the mechanical part is not very good for you to take the computer and go to somewhere else. Right? The vibration on the way can be the problem. Right? I recall that 20 years, roughly 20 years ago, at that time, the laptop, the main problem of the laptop at that time is that they still use a traditional disk, which means if you take it from one location, or we take it and move, then the mechanical part may be destroyed. And together, maybe with your data, right? So there are a lot of issues of that. But nowadays, I think all your laptop using SSD. SSD basically random access, like a memory. In that sense, there is no mechanical part, right? So that's why you can take it anywhere, and so you can even shake it, no problem. But the old laptop, if you shake it, right, very likely it will have the issue with disk. Okay. So this is a traditional rack. I look like. This is a rack. This is another rack. Right? They just put it on top of each other, so save some space. Right? And within this is a cluster within the data center. Right? So there will be a cluster switch. Normally, this is an optical network, optical switch to connect each rack. And you see it connect to this part. This is a top of rack switch. It's basically for networking within the rack. The rack basically is this kind of server. Each of them is considered one U, and this U basically is a unit for the height. Basically, they specify this is the height of the server you can do, and then you can put in a lot of servers there. And within each of the rack, right, is something like this. So the difference compared with a traditional computer is that traditionally there is no GPU. Why? Because there you don't need the display. The GPU on your computer, laptop, mainly is to help your screen, right, to show there. But in the data center, you don't have the screen to show it, right? Therefore, traditional no GPU. Of course, you know nowadays it changed a lot, right? And also, normally the data center, they still have this kind of a traditional disk a lot. Why? Because it's very cost effective. So one server, they may have several this kind of disk. there. So at a server terabyte level, right, for each server.
It's slow to pull data from a single disk. You could unlock it in different portions of the disk, right? You just split whatever data you're using over multiple disks so that you can pull these small pieces from.
Good question. We will talk about that later. So it depends on your hardware situation and also your design. Right? So there are multiple ways to do that. One is that actually, if you have to put the data in the disk, even you duplicate that in multiple one, it won't help a lot because the reading is still very slow. So later, what Google did is that they get more SSD. Right? For example, on the disk, you may have a 10 terabyte storage, but for this SSD, maybe only 256 gigabyte. Right? But still, having that SSD is kind of a catch for you. You can put some data there. And if you make the right guess which kind of data will be used, then you put in the SSD that can greatly increase the speed. Of course, later, like a system like a Spark basically do all in-memory processing. Means that I guess run my system mainly use completely using the memory. Right? So all the data is in the memory. So of course that have a high requirement for the memory size, but the speed is much faster. But if you have to use a disk, right, probably is a way you describe. They divide the data, one file, into multiple chunks. And then you have the opportunity to read from multiple servers of multiple chunks of the same file simultaneously. So that can increase your speed a little bit. Okay. Now data center infrastructure, right? So you can see here, there are several components. Oh, sorry, before that, let me. So nowadays, okay, I forgot to mention, nowadays, the difference is that, right, so this one still there, because you still need to hold a lot of code data. Code that means that not many people want to access, but just in case, that's the reason. But the memory is much larger. Even on your laptop, right, the memory can be fairly large. Right? I think I have a laptop, the memory is 96 gigabyte, something like this. So the memory is very easy because the memory you just have enough slot, right? You just plug them in. And another change is the GPU. Right. So nowadays, data center have more and more GPU server. But the problem is that, as we discussed, one GPU server may take a lot of electricity. Right. So here you may put in 32 traditional servers. But if you put in those very power consuming GPU server, you may only put in 1 or 2. Right? So what do you say now? If you go to a GPU cluster, you will see most of the rack are empty. Because the power there can only support for 1 or 2 GPU server instead of 32 traditional servers. Okay. This is a data center infrastructure. It's just a building. Right? The building is also there. Right? It's something it's hard to change. Why? Because there are 3 main components. One is IT, basically the servers. The other is the power, because the server needs power to run, and also cooling. And while running that, there are a lot of heat. We need to get the heat out. Okay, this part is the servers. There are 2 types of server basically. One is this kind of they call it individual co-location computer servers. So you can think about those are the traditional rack you see. But this is a co-location suite. What does that mean? The data center may have servers that are owned by other organizations. For example, for New York Exchange, the stock exchange, right? They have their own data center, right? They have their servers here, right, to process the data. But many hedge fund, right, especially high frequency trading, they will also hire the space, rent the space to put their server there. Right. The servers or racks technically belong to the high frequency trading company, but they just put it there because then they can get the data a little bit faster earlier than others. Right. So for those servers, you will see they may have the physical lock there, right? And also the fence stop other people getting in. Because you can imagine those servers are running their top secret. Right? So they don't want anyone to get physical access to them. So those ones are also common. You will see these two types of servers. Power. The power is coming from a remote power plant or substation. It's like on campus close to the train station. There is also a substation there, right? Bring the power in and step that down and then distribute out. Similarly here, right? There is a power distribution unit. Right? They go from the high power to the power can be used by servers. And in case there is some failure, right? Then they have this as the UPS, the uninterrupted power system, a power supply system. You can buy those three small UPS by yourself. I can have a server at home. Each one maybe $100. And that's basically a battery. Right? You put there, and if you're out of power, then you can use that to support you for several hours, depending on how heavily you use it. If you go for camping, then that's also useful. Right? But here, it's a big room of this kind of battery. Right? Those batteries can support the data center probably up to 30 minutes. Right? So that if the power distribution unit, that power supply goes down, this immediately goes up. So that you won't have the blackout there. And during the 30 minutes, they have the diesel generator or natural gas generator, right? And of course, they have few tanks or some pipeline get this one, and to cover the power supply, right? For a very long time. Right, this is the power. Cooling, right? So they may have the chiller, they may have outside air. Recently, I heard that they may also use seawater to cool the system. Right? Because now the problem is that for cooling, we use fresh water to cool the system. Right? But you know the fresh water is quite limited. Right? So if you can directly use the seawater to cool it, it's much better. Okay, but think about this one, right? Nowadays, what we are doing is that we are changing this part, right? Putting in more GPU servers, need more power. But all the other infrastructure is already fixed, right? You only have this amount of power supply. So that's why now the challenge is that given the power supply, how to put in more servers. And also cooling is also an issue, right? Cooling infrastructure is already there. So they are capable of cooling the traditional server, but not the GPU servers. The GPU servers, by consuming more electricity, it also generates more heat. Right? That's a challenge for us.
Hi,
Okay,
Professor. I had a question.
Go ahead.
Could you just share your screen so we can see the slides on Zoom?
Sorry, that's a.
No problem, no problem.
Yeah.
Thank you so much.
The Tuesday, don't rely on my performance on Tuesday. So in the other course, I basically I don't do the online version for the Tuesday. It is whenever possible, you should come to the classroom. We still have some IP6 here. So. Okay, now we go to the infrastructure. This is what we discussed. Right? This one, there are quite some improvement over the past decade. Right? Traditionally, we actually lost a lot of power, electricity, just on the distribution. Right? This is the conventional AC architecture. So what they do, they bring the high voltage, 480 watts AC power. That's directly from the substation. And they come here, and then they do the AC to DC conversion so that they can charge the battery in UPS. Because the battery normally you need to go in DC power. And then they go back to AC power to power the system, to go to the PDU. And the PDU go to further step down and do another AC to DC conversion. And then eventually it go to the load. So as a result, this is the efficiency for each stage. It's not that bad. But together, you only get 48% of the electricity actually go to the server. Right? So basically you waste more than half. Right? Yes, you may think about I can improve each part of it, right? Make the efficiency better. That of course costs you more money, right? Because each component you need to buy a more expensive one. But even after that, you still waste 1/3, basically roughly, on the distribution by itself. Right? That's why the old data centers, they are very power inefficient, including many computing rooms, for example, on campus. Right? When they try to get it used to the building infrastructure, it's not easy. But for companies like Google or Facebook, they have their own data centers, and they consume a lot of electricity. They pay the electricity bill, right, very high. So over time, they have incentive to make it better, right? So this is one improvement. Instead of doing this kind of AC to DC, DC to AC conversion, right? You know those conversions, the physics, right, generate a lot of heat, and where you get a loss. But now they remove it. Right? Once they get to DC power, everything just DC. Right? By doing this, they can improve the efficiency much higher. Basically, with 1/4, 76%. Right? Or you can do another way, right? So I just do a lot of AC, right? But they go to high voltage AC, right? So they can make it a little bit higher. The more recent one is that almost everything in the AC, and so they also remove some stages. Right? As a result, they can improve it close to 80%. Right? But still, you lose a lot of power on the way. Cooling. Cooling is a little bit different, right? Because there are multiple ways to do the cooling. This is a traditional way, right? This is the cooling unit, the circulation racks. And this one get the cold water supply basically in the pipe, and then they have the fans to blow the water, blow the cold air down from here. And when the air goes from the ceiling, the floor, and go up, and the hot air comes out, and then cold. Right. So this is the way they're doing that. What is the problem you see here? Something I didn't quite understand is that the physics tell us the hot air is lighter, right? And then if you push a cold water, cold air, then it need to push it very hard so that it can go up. Because cold air tend to stay just on the bottom. Right? As a result, you can imagine on the rack, the servers, the lower you are in the rack, the lower temperature you get. Right? Then you can see the temperature very low just over the rack. Right? That's why later Google did, but all of this is a fluid dynamic, right? It's very complicated. a lot of people try to do the design for it, but it's very hard. Right? Later, Google did something using deep learning to try to solve this one. Right? So in order to do that, what do you need? On top of each of the rack, you need to have some sensor so that you know the current temperature for each location. And given this, you can adjust how you do the cooling. Right? So that's one way. Another way I start to see more and more is that they may have the cold air from the top. Right? That is also okay. And they start to have the fan, very powerful fan, on top of the, in front of the rack. Right? So very noisy but powerful fan just blow the heat out of the rack. Because once the heat is out of the rack, right, whether it's high or low or whatever, it doesn't matter, right? The problem is that you need to remove the heat from the rack. And traditionally, they only use this air to do the cooling. And now they also have those pipe, the pipe of cold water inside the rack. Right? So that within the rack, you have some very cold water pipes there. So that when you blow the air there, the cold pipe also can help you do the cooling. Of course, the most advanced technology is the immerse cooling, right? Let me try to see if I can find a photo for that. Oh, how to spell the word immerse? Liquid cooling. Right? Oh, yes, thank you. Let me see if I can get a video.
We need to tell you about Beth's IUD. Beth got it a couple of years ago to treat her endometriosis,
Yeah, something like this. So everything just in water. It's actually not just water. Take a like liquid. This liquid is used to clean the server, but now they just directly dry it. People also think about use some particular oil for that, because oil, you know, it's not a conductor, right? So it's safer actually to use oil. But anyway. Okay, so there's a lot of need. At the same time, they create a lot of technology, new technology. Actually, there is a change, right? So from 2010 roughly to 2020, data center almost stays same, like what I showed you here. It's only in the past several years people start to put GPU in data centers. Because traditionally, even though GPU can be used for parallel computing, but the demand is very small. And then this is the cooling tower, right? So the cooling part, cooling also take a lot of electricity. So there are different ways of doing this. One is do the free cooling, right? So they are building some data centers near Arctic. Right? There you just blow in the outside air in, and it's very cool. The other way is to use the water cooling, right? So Microsoft, they put one small data center. It's basically a container, right, with the servers into the bay in the Bay Area. And it runs perfect, no problem for running it. Of course, the people also argue that whether it's good for the environment or not, right? Because actually you generate a lot of heat. The heat is a double-sided sword, right? So it's good and bad for the ecosystem at the same time. Okay, so basically, from the power energy, right? Building those one, also the modeling, there are a lot of challenges. Right. Actually, some challenges are not unexpected, right? Like the power supply we discussed, right? When data center, because you know for each data center, the lifespan when they design it is 20 to 30 years. Right? So that they already have a lot of buffer inside one. But still, right now, the rapid increase in GPU servers and its power consumption make a lot of the data centers the operation very challenging. Yeah, that's another example highlighting prediction is very hard. Especially you predict for 2 decades, right? Who knows what will happen in 2 decades? Okay, compare with data center with your own computer, laptop. There are some differences. The first is a high level of parallelism, even in the old ways. You can think about in the old way, the parallelism mainly come from the CPU, multi-core CPU. And each server may have 20 cores. Right? And how many servers they may have? In one data center, they may have 100,000 data centers. Sorry, servers. 100,000 times 10, 1 million server million cores they have. Right. That means they can, if you have a small task, they can prioritize the task in parallel, right? In the level of hundreds of thousands. Right? Versus our laptop, right? I guess if you have a powerful one, you may have 8 CPU cores or 16. Right? That's probably already fairly powerful compared with that. And nowadays with GPU, that's a very different story, right? Because one GPU gets thousands of cores. Each core is not powerful, but you have thousands of cores on one GPU. Right? You can think about how many GPUs they have, right? Together. Also the diversity of workload. This one actually changed a lot. Right? On your laptop, I bet you will use at least maybe 20 or 30 different type of workload. The applications you use very often. But in data centers, they have tons of workload. Right? And they also change over time. For your own laptop, probably it doesn't change much. If you like one type of game, you may use it for many years. You may have a different version, but the same game. But in data centers, right? Think about it, it's already changed. Right? In the old days, MapReduce is the main part. Right? To do the like a Google search, right? To do many other stuff. And then we go to the social media, like Facebook, other company. And then they have a different application, right? They have something called map cache. Partially handle the problem you just mentioned. I don't want to put everything in the disk, it's so slow. And also synchronization become a problem. Because you don't want to happen is that on one computer, you become a friend with another user. But it takes half an hour for another computer or another database to realize it, because it's a distributed database. Nowadays, it's quite synchronized. It's much faster. Later, it go to something like a Spark to do the data processing. And nowadays, as you know, go to large language models. A lot of data center, basically the GPU are just running the large language models, in particular transformers. Go ahead.
Generally, is Spark a good medium for low inference, real-time location services or real-time API endpoints?
Yes. I think the main selling point at that time is that they process everything in memory. Because the baseline at that time is a Hadoop system. The Hadoop system, the problem, later we will show you the detail. But the Hadoop system is that once they get the intermediate result, they write it to the disk. And the next stage will read from the disk. Guess why they are doing that? Disk is very slow, right? Right? It's a failure. Once there is a failure, I already put it in the disk. For Google file system, in particular, you're writing in 3 disks. Right? So if one of them or 2 of them goes down, I can still get the data. But if you write it in the memory, right? If the server is down, basically you have nothing. Right? So that is also the challenge for Spark, how to handle the system in the memory, because memory, when you lose power, you lose everything. Right? So that from the failure reliability or resilience, Spark is a much higher requirement. But the benefit you get is that you don't need to go through the disk read and write stages. That is very time consuming. So you can directly read and write from the memory. I think we have yeah, I can jump here to show you something, right? This shows you the latency, right? You get from the local memory, right? Latency. It's like a microsecond, right? 0.1 microsecond if you read locally. But if you read from a local disk, it's several megabytes. Right. That's why that's highlight the benefit you get by reading from the memory. Go ahead.
That's those that latency speed compared to say 2 nodes talking to each other within a
This will also show you, right? So this is like you get another server in the same rack. The device is here, but it's still much faster than you use a local disk. And also this one, I think is an old technology. Now the communication become much better thanks to the recent development of GPU cluster. Right? Because the high speed communication was once used in high performance computing, right? Like a local BL, Brookhaven National Lab, or Sandia National Lab, Oak Ridge, right? They built a very large supercomputing center. And there, for example, they do the nuclear simulation, right? They want that to be as fast as possible, right? Also, they don't have the budget limitation, right? Basically, the government funded, and so that they can afford the very expensive technology. For communication, that is infinite band. And infinite band is probably 100 times faster than the traditional Ethernet, right? Now with the GPU server, I think last time I showed you the DSG, right? From the NVIDIA. For that one, they basically use infinite band, similar technology. They give a different name called NV switch, but it's almost the same. High speed connection. So that they have 8 or 16 GPU. Among the GPUs, if you read the data, read and write the data, so it's much faster. So that basically means that the memory you use here is all for you, right?
context of like training extremely large neural nets. Does that mean there's not really any sort of loss in latency if you were to split like the neural net into subnets and training one type of teams that talk to each other? As compared to like making one gigantic single node and training up there.
First of all, we cannot make that gigantic node because the model size grew much faster than the memory size, right? Actually, for transformer, you can ask for arbitrary large model. Second is that it helps a lot, but it's still worse than you have your everything local. Because within the same GPU, you read your local memory is still much faster than you read a local one, right? But not the same one. Okay, come to workload, right? So in the future, I think the NVIDIA, for example, they try to argue that the future architecture of data center is like So everything income, this is a large language model. All the requests. Nowadays it's different, right? Nowadays is that there may be different type of applications. Each one serve a different type of workload, right? You go to there. But the imagined future is everything come to the large language model. And then this one will decide which kind of a model you go to. And many of them are again large language model or large model, or they call foundation model, whatever. Right. Whether it will become the case, we don't know. But at least what we see is that we see more and more neural network model workload in the data center. Results heterogeneity, right? So your computer is just one computer, right? But in data centers, they have a different generation of servers. Right? Nowadays, they make it even worse, right? They may have the CPU racks, they may have GPU racks, very different from each other. And the failure is a no. Right? It actually become a little bit better in the past. Right? Over the past 20 years, as I told you, when they built not 20, roughly, right? From Google started to build their own server, their own data center, to like 2020, before the GPU server. The server becomes more and more cost effective and reliable. Right? You can imagine, especially by the ending of Moore's law, kind of not ending, slow down. Then we no longer build those very powerful CPU. Instead, we do multi-core. As you know, if we push the frequency very high, at the same time, you also push the temperature on the chip very high. So it's more likely to have failure. But now we have multi-core system. Each core is not that complicated or powerful, right? Then actually it becomes more and more reliable. So that if you look at the failure in data centers, most of failure is actually software failure. All the infrastructure, right? You configure the system wrong, right? That is more likely to be the failure. Instead of the physical hard drive or some GCPU go to failure. But with a new GPU coming in, right, the hardware failure again becomes the problem, right? Because the GPU, especially NVIDIA GPU, come with both hardware and software failure at the same time. Right? On the hardware side, right, one indication is that the company delayed the delivery of the next generation of GPU because in their design, there was a mistake. This is very rare in the history of the company. Right? But why they are having this? Because on the one side, the chip become more and more complicated because people push to the limit. You can imagine you build just a okay GPU versus you build the most powerful GPU. Of course, the second one is much harder to design. You need to pack more stuff on the same GPU, right? The other one is that they are eager to deliver the next generation GPU more sooner, basically. Previously, they have plenty of time to design and to check, right? But now they don't. Right? All the companies are basically waiting for their new, more powerful GPU. Right? So the GPU is more likely to have issue. Right? This is something we see, right? Of course, there will be many issues in the GPU we didn't see, but it will happen. Another problem is that the software. The software, because you use a GPU, use a CUDA, right? And combine with PyTorch or whatever to do that, right? So there are multiple layers, and it's complicated, more and more complicated. So you should expect more errors from it. And also when we do the large scale training, for example, then if you do the large scale training, right, then you're more likely even one failure on one GPU, that may cause a problem, right, on the whole training. And it's not very easily that you just discard the data on that GPU, right? So for MapReduce, especially for Google search, say if they get 500 tasks going out to do the Google search, and only come back 99% of them, 5 tasks actually stuck there or going nowhere. They can just discard the 5 tasks, right? Combine the remaining 495 results, give you. You're probably happy enough. Actually, you cannot tell the difference. But current training, probably you don't want to discard the 5% because you probably rely on that for your performance to be a little bit better. So failure has been a norm and will still be the norm. It's just now we don't have enough experience handling those failures compared with traditional CPU servers. People already develop a lot of technology for that. The next one, communication dictates performance. Think about there are multiple components that can affect your performance. The first one is a computing speed. At the early stage of computers, that is a key. That has been there for decades. That's why Intel tried to get you more and more powerful CPU. I can imagine that when I was at college at that time. So the performance of your computer basically depends on the performance of your CPU. If you have a low performance CPU, other part cannot help you because the CPU is a bottleneck, especially when you play a game, right? At that time, we don't use GPU acceleration a lot. So mainly use the CPU to do the processing. Therefore, if your GPU is not fast enough, you cannot play the game. And everything is slowed down. And that changed almost the same time when we have multi-core. And then suddenly, CPU is no longer the bottleneck. Whether you have 4 cores or 8 cores, doesn't matter that much, right? For example, if you check your CPU utilization on your laptop, you will see most of the time it's very low. But in the old days, even you are downloading a file, your CPU utilization might go to 100%, highlighting it's a bottleneck. Right? And after that stage, right, CPU no longer is a bottleneck. What is a bottleneck? Right? On our computer, normally the next one is the I/O, when you write and read to your disk. It's very slow. And later, you have SSD on most of your, if not all your laptop. That also becomes faster, but still, that is a slow part. When you go to a data center, the I/O definitely is still bottleneck, but the communication is even worse, right? When you send data from one location to another, right? For example, try to send a video file from one computer to another. Take a very long time. Right? So communication now still the bottleneck, and it will remain the bottleneck for a long time. Why? Because CPU or GPU, it's more like an individual one. Once you increase the speed of a server, or each server, basically you're done. Right? Disk is similar. If you increase the speed of the disk, right, or the memory, increase the memory size, you also can solve the problem. But the communication, if you have n servers, your communication complexity is on the order of O(n) squared, right? Because each server can send data to any others. Right? But that's a problem because you have a lot of servers. Right? If you have a 10,000 server, right, the square is huge, right? So you cannot technically, right? You can use infinite bound to collect 8 or 18 GPUs. But if you have 1,000 GPU to connect it with NVLink, it's very costly. Right? So you should expect that the communication is still the bottleneck. Right? So I mean that's a interesting part. Even though now we have the more GPU servers in the data center, change a lot, but those differences still hold. Right? This is more like a more fundamental stuff. Okay, for software part, we are running 3 categories of software. The first one is platform level. Right? So you need to install something on each machine. Right? For example, Linux. You need to install that one. Otherwise, you cannot use a server. For this is basically the local operating system. the goal for the operating system is enable you to use the resources, basically, right? So you need that software, otherwise you cannot use. But something different, this one you also have it on your own computer. But this one is new, right? This one is a cluster level, right? The distributed system allowed you to use the many servers at the same time. Right? Clearly, we don't have it on our laptop. Right? For example, if there are 20 laptops here, to run a job across a 20 laptop is very, very hard. Right? But this one is a class level, like Hadoop, Spark, right? Kubernetes, something like those are mainly for this purpose. Right? It's basically adding another layer on top of your individual operating system. It's a basically considered as a cluster operating system called network operating system that allowed you to use resources on multiple servers at the same time. Finally, on top of that, it's an application level, right? The user-facing application, for example, ChatGPT. Right? It runs on top of the cluster level, right? And then on top of the local, probably Linux system, and also combined with their CUDA system. Any question? Yeah.
System scale, right? Some of the things for, on what level are we talking about? What's the most likely?
Anyone guess which one?
Division.
No, this one. Last year. Why? Platform level. What do? You just install the software there, right? If you can do that on your computer, you can do it there. Right? So you shouldn't expect a lot of issues from there. Application, similar, right? If you can use ChatGPT on one server, you probably application level is similar. But the middle part is a problem. The middle part is something very unique to data centers. Only you see there. And it's very complicated. For example, you train a model. From your part, it's very easy. You can just write, say, I have a transformer model. This is how many layers. This is given the parameter. But the system, if you need to go to multiple servers, then this one, they need to decide how to split your data, how to split the model in some cases, and how to do the computation. What's going on when you have one of them slow in response or have failure? A lot of things you need to handle. And those of them, first, it's complicated. Second is that we don't have enough experience. It's just in a data center. Right. That's why a lot of failures actually happen from there. You will also say, okay, I'm not sure our assignment will give you enough exposure, right? But for example, for Hadoop, you can install Hadoop on your own laptop. It's called a standalone version. Even though it is a cluster level application software, right? Allows you to use multiple servers. You can just install on your own server as a standalone version. This one is very easy to install. Almost no issues. Right? But once you go to multiple servers, right? If we don't give you the instruction, I bet many of you may struggle about how to handle the failures. Even the configuration, you need to write the configuration files for many of them. Right? And what we give you is a simplest case and has been there for decades. Right? It's still non-trivial. Right? And then if you try something like Kubernetes, using GPU servers, right? So you expect more issues. But again, if you just do that on your local computer, just one computer, very easy. Because it's similar to install another kind of you can consider either platform or application software on your computer. But once you go to beyond one server or one machine to multiple, you have all the complexity. And then the more servers you get, the harder it is to manage. Of course, in our project, you don't have you can consider you don't have the luxury or the trouble, right, to manage a large cluster. Right? But you can imagine, in your case, you probably need only 2 or 3 server, you can do that. But think about if you have 1,000 server to do that. Right? So some of them may have failure on the way you run it. But if you only have 2 or 3, I bet when you run the experiment, most cases you just directly get it. You won't face any failure. It's more like running on your own laptop. That's why, right? A lot of things going on here. I'm trying to find the issue in the class lab. And okay, this is also what we will mainly talk about because the platform level, right, is similar to what you have there. Now, common technologies used in data center, right? This is a table. Oh, by the way, we have the quiz next Tuesday here in person. Yeah, I guess some student we need to find outside. I saw some chairs as well, right? But I think we should be able to do that. The quiz is in person. Whether you select the which section, right, which course number, right? As long as here, the quiz need to be in person. It's too hard to manage the online quiz. During the pandemic, we did some of them, but it's not easy and it's not good. So for the quiz, right, it will all the quiz are multi-choice questions. Right? So that's a good news for you, hopefully. It will cover material until this Thursday, so including this Thursday, or everything on the slides. Of course, right? I also explain some of the slides. I expect you know some explanation as well. Okay, for example, this one, you can expect that there will be some question about this one, right? Because there are so many techniques that they can easily ask you a question. Okay, so we can go.
How many questions would be there in the book?
10.
And all would be multiple choice questions?
Yes. So if you follow the material closely, then it should be very easy for you. But the previous years, the average is around between 70 to 80. Later it increase. Normally the first one is the hardest. But once you get used to it, it's increased a little bit. But don't expect you will get all the questions correct. It's actually hard. Partially because, right, for some students, you don't have the right background. Right. So that's why if you have questions, you need to ask me now. Right. If you just feel like you understand it, but then when you see the question, you will start to struggle on which one is the right answer. Right? For example, here, this is what we have for the different techniques, whether they are for performance or for availability or reliability. Right? I will explain one by one. Right? So first, replication. Right? It's very easy to understand right from the name. You just duplicate the data, right? All the tasks. Of course, it increases your performance. More clear is that increase your availability or reliability, right? Because in some field, you have a remaining working copy. Why is also help with performance? That's what you explain, right? You ask. If I have 3 copies, then if I have multiple users read the 3 copies, say I have 3 users, I can ask them each to read 1 of them instead of waiting for only 1 copy. Okay. So for Google file system, it's actually the underlying philosophy like this. Of course, if you know the system, if you have experience with distributed system, you may notice there is an issue actually with that. When you read the data, actually you benefit, right? But when you write the data, you suffer. Because you also need to write 3 of them, right? So that's why Google file system using this technology. It's mainly for the system that you do a lot of read instead of write. Right? For Google search, most of cases you just read the data, right? You don't write data. And the only case you write the data out is basically you update the web page or you find some new web pages. Right? But those ones you can do during night, for example. But you don't have a lot of workload. So it's not a big issue. Right? But for other applications, for example, social network, you may write a lot, right? Then it may not be the right strategy for you. Right? In that case, they may use something called eraser coding. This one is a little bit different, right? The goal is that, say, if I have 5 copies, not 5 copies, 1, 2, 3, 4, 5. Let's say 5 chunks for a file, right? Instead of copy each of them, they can do some mathematical calculation, right? This is so-called this coding. For example, I get 6 and 7. So from the calculation, from here, you generate these 2. And among the 7 of them, as long I have 5 of them, I can recover all the information. Right? This is the property from the coding scheme. Right? A lot of math behind that, but it's beyond what we want to cover. But you basically get to know this is the eraser coding. So in that case, it also increases availability. Right? But the impact on performance is a different color. It's hard to say. Right? So this is more like the case for Facebook, because a lot of user data and a lot of write, they don't want to duplicate all the time. It's also especially if they want to put the data in memory. It's a lot of data. Google is different. Put it in the disk. Right? It's very cost effective. And also for the computation, right? Later, when Facebook become popular, the CPU computation is already very good, especially in multi-core. Therefore, this calculation to generate the additional data chunks and also use them to do the recovery, it consumes more computational resources versus the I/O resources of read and write. Right? But they can afford it because a lot of CPU cores here just idle, waiting. Next one is sharding and partitioning. Right? It's for both data and for workload. For data, after given a file, they cut it into multiple chunks. Right? And for the job, they also cut into multiple tasks. Right? So by doing this, it actually improves the availability. Right? In the sense of if one chunk goes disappear, you still have the remaining of the file. You don't need to recover everything. You just need to recover that particular chunk. Similar for task. If one task disappear or stuck, you only need to reproduce the result from that task only. You don't need to rerun all the tasks. Performance, it also makes it better. Right. So for example, with multiple chunks, you can read the file at the same time. Right. If say this is a file, if it's a single file, you can only read from one server. But now if you put it 5, and on 5 different servers, you can read the 5 chunks of the same file at the same time in parallel. Load balancing, right? So you can imagine so many servers, the load on each server is different, right? So if somehow you can balance the workload, right? So that no user is overused. Overuse means that the performance may suffer, or some servers are just waiting. You can improve performance. But in this case, it's nothing to do with availability. You do load balances. So health check and integrity check, it's basically check what's the status of the server or the task. Right. So there is something very common use called heartbeat. So for example, every minute, the master node will send to the workers a message, ask the worker to reply. The reply just say, I'm still alive. This is so-called heartbeat. Of course, with the heartbeat, you can carry additional information, right? But at least from this health check, you can check the availability of the server. So that if you see one server is not available, basically stop responding, you can basically start to do the recovery of the server, right? Later we will show you more details, but the high-level message is that if you realize one server not responding, then you can start to have multiple other servers have the same data. You create the backup or the recovery and start to send data from other servers on that one, because the data recovery is actually the most time-consuming part. Right? Consider each server, it may take a 10 terabyte of data there. And you can do the math, right? So this link normally is 100 MB per second. Right, so it takes a long time to recover the data. Go ahead.
Does this automatically start data recovery?
Yes.
Even before the system, even for like the broken servers, it says.
Yes. So that is based on we discussed failure is a known. When you say failure is a known, whenever you say something goes wrong, you would rather be conservative saying it goes wrong. Right? Then you start to do it immediately instead of waiting. Right? Of course, it's possible this server just some network issue. The package got lost somewhere, right? It's possible. But because you take a more conservative stage, right, then you just do the recovery immediately. Right. Actually, another property of data center I didn't mention probably is that there are not many people in the data center. Right. It's different from the computer room. Normally, no matter how small the computer room, you need to hire someone to take care of. Right. But for data centers, they may have hundreds of thousands of servers, but they only may hire 10 engineers there to take care of the data center. So from that perspective, the personnel cost is very low. As a result, if you need to wait on someone to go over to check it, you may need to wait for a month in this case. Right? Because actually, when they feel like this field is not critical, there are so many servers there, they don't worry about it. Right? Because one personnel, the cost is too high, right, compared to the servers. Right? Because you need someone experienced, the pay salary is fairly high. Right? So they are doing this. Of course, nowadays it may change a little bit, right? Because if you have the DSP more advanced GPU server go down, you actually don't have the luxury. You have many of these kind of server to kind of restart from others. Right? In this case, yes, you may have the personnel to check, to fix it as soon as possible. That's because each of these is too expensive. Right? That time we saw each of those servers may cost you 200,000 versus each of the rack server may cost you 1,000. Right? That's the difference. So 1,000 go down, that's fine, right? But this is very expensive one goes down, you'd better send someone to fix it. That's the difference. Compression. Clearly, compression is used for performance, right? A lot of data is compressed, right? But it doesn't help you with availability. Right? So the interesting part about the compression is that people were thinking about two options. Let's say from Seattle to the Bay Area. Right. There are two options. One, you use the truck. The truck is loaded with the disks. Right? You can send the data actually from one location to another, right? You just send the disk physically there. And you put them there, then you get the data. Or you send them over internet. there was some calculation, right? Depending on how much compression you get, right? In some cases, using the track is a better solution. It's a faster. Right? When you have a lot of data to send. Now you can do the calculation, right? Each hard drive is can take a lot of data. And you send the content over internet to another one. Right? This is more like right? These are two data centers. To do the synchronization for the data centers, especially for cold data, it's better to ship the disks right? Instead of send over the links. Because sending over, actually, they charge you money. Last time I think we didn't do that, but let me show you guys. Okay, so this is a data transfer cost. Right, so this is old days, but
Pricing, you scroll down. The price.
yeah, this one, right? The pricing. Okay, let me see if they have it here. All right, so later, next time I will find it for you. Okay, so basically means that actually the big issue nowadays when you use one cloud, for example, you are used to AWS, but now you want to move to Google Cloud or you want to move to Azure. The big issue for you is that how to get the data out. Because in many cases, actually, when you send the data in, they don't charge you, or they charge you a little bit. But when you send data out, they charge you a lot, and they try to lock you in. So basically means if you want to send from one data, the Google data, the Amazon data center to Google data center, right? So you may have a lot of data there, that may cost you a lot. Right. So similarly, right? Compression is basically used to be here, right? To compress the data, right? Before you send that. And the compression, you think is a trade-off between the network or the communication and the computing, right? So you just use more computing resources to save more communication. In many cases, actually worth effort. I think in Hadoop originally, in many cases, they can compress the data for you, for intermediate data even. Okay. This eventual consistency, basic idea is that I don't need everything to be consistent all the time. Like that is a strong consistency. But to have strong consistency, that means the performance may suffer, right? You need to wait, you need to do a lot of things. And also availability may also suffer, right? Because whenever you say something are not synchronized, you may consider as a failure, and you need to handle that. But the eventual consistency means that as long as we eventually consistent, we're okay. For example, the data center for Google search, right? The material in one data center may be different from the website from another data center, right? In this case, actually, they will become eventual consistent. I'm not sure, right? They may not be consistent all the time, right? But it's okay. In this way, they make the availability better because even not consistent, you can still use it. And the performance also better. You don't need to wait. You don't need to do a lot of additional handling, right, to make it a consistent. But the limitation is that you cannot use this kind of a system for example, for financial application. Right there, you probably want to have a consistent all the time. Actually, some interesting example is a blockchain, right? Like Bitcoin, they use a blockchain technology distributed to achieve the consistency. And there may be some issues, right? So you may heard about a double spending or something like this, right? If you're interested, you can learn those. But here, you want to know in data centers, in most cases, we don't require those very strong consistency that benefit both performance and availability. Centralized controller, right? In many cases, we still have the centralized controller, right? It's benefit the performance, right? But it's clearly it's not good for availability. It's just make the system simple. Canaries. The canaries, what they do is that they often, before releasing a new version, they often run the new version in a test data center. Or in the data center, they have something for production, something for R&D. Right? They first deploy them there. Say that R&D data center may also have 10,000 servers. They first run them there. If there's something goes wrong, not a big deal, right? You can fix it. Once they are confident, they actually go to the real production. They have a 1 million server to run the system. So clearly, this does not do with the performance, but it helps with availability. Because if you have some bugs there, and you directly put it into the production system, the system may go down. Right? So they are doing another kind of real-world testing before going to the production. Last is redundant execution. This is one for MapReduce. In this case, for the example I give you, one job I divided into 500 tasks. Right? I put the 500 tasks onto 500 servers. Guess what? 99% of the tasks will come back very quickly. And then you may wait for the remaining forever. Right? It may be from you are not doing the right load balance. Right? Actually, those several tasks actually contain most of the computation. That's possible. But the more likely is that those servers may go down or something. Right? So instead of waiting, so you will set a threshold. I say, whenever I only have 5% of tasks left, then I just duplicate all the remaining 5% tasks on multiples of other servers. Right? The hope is that if we start here because the server is overloaded or there's something wrong, then I can rely on the other server to get the result faster instead of waiting. Again, this is based on the assumption that failure is a null. Right? So if you see something does not seem good, the better bet is a failure. Right? Instead of optimistically think it will eventually come back. It may come back, but it's safer to just duplicate, do this redundant execution. By doing this, they show that actually it improves the performance a lot. But it does not do with availability. Okay, I will stop here. And a reminder, I sent the assignment for the group members. Sorry, I actually put it in the assignment last week, but I forgot to make it visible to you guys. Right? So by the end of today, submit the group member, and then we can start with the next steps. Okay, so that's end of for today.